So now we already know that this cannot be irreducible representation because we already shown it's not irreducible representation for a subgroup of SO3 just rotations in a plane. So now we have to figure out how to find irreducible representations for non-abelian, that is to say, non-commuting in various directions groups. There is an idea which is different than anything we have done so far in it. And then there is a technology of implementing it. So let me try to share the idea, verbally. See whether it makes sense to you. It is possible, and there is an amazing book which you can steal on internet that actually does it, to use just Hamilton-Cayley equations and get all these guys, all this representation, without ever constructing any eigenvectors and going to particular coordinate choices. But this is not how the history of the subject went. What they realized at the end of 19th century, Killing, I think, and Cartan, I don't know whether somebody taught Killing this, but that's where I've seen it first in reading the literature. When you solve these problems, there is a natural coordinate choice in which you only operate on integers. So you have coordinates and you can describe irreducible representations in these new coordinates in such a way that every irreducible representation is characterized by a set of integers. That's called a lattice. Now, we have already seen a lattice, but we didn't make much out of it, which is we have seen that when we go to irreducible representations, so our angle is a continuous number, real number, that goes from 0 to 2 pi, but it's on a compact domain. The irreducible representations, which are how that compact domain rings when you hit it and see what its oscillations are, the standing waves on the domain have an integer number of modes. So, what we learned here is that configuration space, space of shapes, like when we were looking at finite groups, it was like a triangle and you were doing something. So it was this all distinct, in general, n factorial possible permutations of vertices of something, finite number of points. But now that we're in continuum, we parameterize it by one number. So there is a phi, and it goes from 0 to 2 pi. And then 2 pi plus epsilon, you started on a new circle. So when we now go to reducible representations, for finite groups, what we had is we have finite number of points, and we had finite number of reducible representations. But now in a irrep space, the simplest example is wave number or momentum space for SO2, but in general, we get a lattice of solutions. So we'll get a trivial representation, do nothing, or rotate to the right, or rotate to the left, or run twice around the circle to the right, or once to the left, and so on. This is so simple that you don't appreciate it, but there is a little interval here. And if you understand this interval, then by repeating it, you can tile the entire infinite line. So if you understand what the basic tile of the system is, you can tile the whole lattice of possible states. So that's the simplest example, one parameter. What we'll do next, and people who have taken quantum mechanics courses have gone through this, and I'll give you as a reference Dr. Sherbakov's lectures because he does this very nicely online. For more parameters, so morally, you think of planet Z, where we have more parameters. It immediately gets a little hard to visualize because I don't emphasize visualization because we'll have 3 parameters of rotations. So it's not just the surface. So you have to think a little harder, but for purposes of this is good enough. So more parameters. We'll get is in a dual space, we'll get a lattice. So it'll go in various directions. And it's kind of lattices that we have already seen when we discuss space groups, the infinite dimensional, but it's not quite that kind of lattice. So, it's something that's called Cartan lattice. And if you're able to understand the basic tile, integer multiple that label representations. Once I taught it honestly as a course, as a mathematics kind of course, and it takes a semester or half a semester or something. So it's not worth our time here. We just have to understand, what's the basic idea, how it's done, and then we'll check it. Just like we did for finite groups, we check it for triangle. Here, there'll be also a triangle, but it's called SU2. Basic idea is when you have a compact group with more parameters, it's irreducible representations which correspond to wiggles, but integer number of wiggles on this compact space in different directions. Can be labeled, have names which are essentially counted how many times you wiggle in various directions. And that is the essence of work of Cartan and Killing at the end of 19th century. Now I'll do stuff that kind of standard and boring. I won't do it very well because it's standard and boring. I'll do it for SO3. And once you do it for SO3 and SU2, you have in principle understood everything, but really doing it honestly requires a little bit more thinking. Remind you one more time, it's a continuation of this line of thought. There's some representation that makes sense to you because you have intuition about it, but the correct ones are actually something with complex numbers and phases. So this will now repeat for SO3. There is no pretty way to do this. So I'll do it in a way that people do it when they teach quantum mechanics. So the basic idea is we would like to find eigenstate, these M's, these eigenfunctions, such that when I bang any operator on them, I get a number back. What happens when you have more than one dimensions, you have more than one operation, so things don't commute. So you have to find your central algebra, like we did for finite groups. You have to find the number of commuting operators. You can use them successively to reduce subgroups to smallest ones, to representations to smallest irreducible ones. So you have to make sure you have them all. You have to make sure they commute. And then you use Schur's lemma in the same tricks as we did before. You do this for Lie algebra. Often when people write SON, they mean group. And when they write it in lowercase n, they mean algebra. So this is Lie group and this is Lie algebra. And the strategy in the subject is always to start with algebra because that is set of finite calculations that we know how to do, and then promote them to the group. And it turns out promotion to the groups is non-trivial because some of the representations are double covers and other stuff like that. So the first thing is we know that if we can take any of these guys, let's say we take any of the vectors, let's say JZ, and we can use its Hamilton-Cayley equation if we figure out what it is, or some other trick, to get integers, which we'll call M, in the integer set, meaning that they run over. But then we need another thing, and we are allowed to do anything we want to with our generators. Thing that's always commuting is any one of these generators that generate rotation in different direction. Is something that's called Casimir operator. Idea of Casimir operator is that any generator J1, 2, 3 generates rotations around the 3 axis or more if you're looking at larger dimensional spaces than 3 dimensions. In this particular case, these are our 3 dimensions, this number 3. An idea of Casimir operator is that when something rotates, it has its total momentum, but when you look at it in different coordinate frames, you're just seeing one of component of that momentum. And in physical systems which are translational invariant, the law that we care about, the translation invariance, but also not just homogeneous in space, but also isotropic. So all directions, isotropos, directions look the same. Then the one defines this object commutes. Why does it commute? If I take J squared, this operator, which is, remember, just a matrix squared, we're not afraid, and it's a sum of 3 matrices. We know how to compute it in any given representation. I have to compute commutators with these 3 terms. The commutator with the term itself is 0, no problem. And the 2 other ones get exchanged, but I have a sum of them. So, what happens here gets exactly canceled by what happens by the other term. And I verify that this is 0. And for SO3, it turns out to be all you need. When you go to higher dimensional groups that describe rotation in higher dimensions, you might need more of these operators, and there is a way which you can, for example, see in my book. You can construct all of them. You can always construct this commuting set. Just depends on the algebra itself. It doesn't depend on particular representation, making sure you have enough. So now comes a little bit of the trickery. That's the only new idea that enters here. And the trickery is, motivated by these notions of going to lattices. The idea is quite simple. So it was a problem that, some of you found confusing. I asked you to find Clebsch coordinate series when you take 2 irreducible representations of rotation in 2 dimensions and find that any direct product of representations is reducible in general, even if the bits themselves are reducible. And here it was extremely simple because it meant that you just found a representation which was, if you had the first and third, you multiply them, you found out that the result was irreducible representation 4. In other words, you're just adding things along this lattice. The basic idea of the trick I'll show you now, but I'll suddenly go to non-obvious basis, was that this kind of addition rules should work in all directions. So you have to figure out how you add this way, but you also how you add that way in integer steps. Crucial thing is that you are relating integer sites on a lattice. And this trick is what classifies all Lie algebras, semi-simple Lie algebras. Simple means you can split it in separate pieces. Semi-simple says you can split it in a simple way. And the trick is to change your basis from Hermitian to complex. So you define new operators by simple algebra that say that if I'm here, I still have to deal with x and y. So you combine them as you would combine. Remember, Hermitian matrix is a generalization of real numbers. And now you go to a complex version of them by multiplying the second Hermitian matrix by y. So this is no more a real number. It's not a Hermitian matrix, but it has a property that if I take a Hermitian conjugate of it, what happens is this one doesn't change. This changes sign. This one doesn't change. So under Hermitian conjugation, they behave like complex numbers behave under ordinary complex conjugation, meaning that this sign changes plus minus y. So Hermitian basis was J x, J y, z. This one is special because you're using its eigenstates. It rotates in one direction. So using the result that we had before, that on a circle, the grand circle now, you have integer number of eigenvalues. But now you have to account for action of these guys, and they're not commuting, so you have to do something, and it turns out that's a trick. Are you still with me?
Yes, it appears so.
Oh, everybody's here, sort of. These guys have names. Rising operator. You have seen it if you've taken quantum mechanics course, but if you apply the operator on eigenstate of the z operator, the third one, this one is composed from x and y rotations, and then you measure its momentum, you can multiply it out, x plus or minus I. Now you can use the commutators. We make this into commutator by adding and subtracting these two guys in the opposite order. This is the commutator, and this is the leftover. The commutator of these two guys, and now very important sign, so you guys correct me. So this is this guy. Now this is plus jx, but z acting on its eigenstate just gets replaced by integer m, so that's this term. And there is a plus minus I. This, I think, gives me a minus sign. And this gives me integer m. All of this acting on eigenvector m. M is multiplying, this x plus minus y. But that's what I call raising and lowering operator. And I have an I times here also y plus minus m. So I get in other words, a j plus minus m. This whole thing here is giving me eigenvalue that corresponds to next state. So we have that m . plus 1 equals, or minus 1, depending, is the result of this operation. So it's raising and lowering. That looks a little funky, but it's actually powerful because that's how it's going to work for all semi-simple Lie groups. We now understand how the eigenstates of the J operator work, but I told you we should also find out the values of the commuting guy. And if this gives me a separate label, that will be important information about the eigenvector. This is Jx plus c squared. Due to the magic of complex numbers, I'm allowed to write the first two guys as Jx. So I was told that, on the test to measure the aptitude of incoming class at Georgia Tech, they all arrive as 100% grade averages because of the advanced courses that I've taken. So they all are above average. And like Swiss cheese, they always ask if I have a minus b squared, there's a multiple choice question. This equals a plus b. And I don't know what. I can't even imagine. 4 choices. They guess this guy, this answer with 25% probability. Statistically, even, but we're using this fundamental identity here, that 1/4 of our undergraduates' guess is correct. But we have defined this, guys. This is plus, this is minus.